Okay, so today's presentation or webinar is just about bracing design and installation. So as I mentioned, I'm the engineering manager for Australia and New Zealand, and been with Pryda for about 19 years. And my key role function really is to promote and educate efficient engineering design and compliance requirements to our customers and their builders. And that's part of what the webinar today is around. So who's Pryda? For those who don't know, we're a part of an ITW, which is a global company, and we form part of a group of companies that supply products into the building sector. So essentially our core market is timber roof and floor trusses of wall frames. We provide technical support to our customers, so we enable engineering design software, engineering and software technical support, frame and truss manufacturing equipment, and we also manufacture and supply an extensive range of timber connectors into the building market. Okay, so today's presentation really is going to cover three main areas. Essentially, the first part is going to be understanding bracing methodology and design. Then we're going to move on to some of the site fixing requirements of the bracing units and other systems to stabilise buildings. And then we're going to look at some common site installation issues after that. So if we look at the legislative requirements, the legislation for bracing design is governed by the NCC 2019, and that calls up as part of its remit the AS 1684, which is a deemed to comply component of the NCC. So essentially what that means, if you follow the prescriptive nature of the 1684, then you automatically get building compliance by following those provisions. Okay, so that 1684 document is targeted to Class 1 and Class 10 dwellings, which are essentially either single standalone dwellings or rows of townhouses and attached villas, so residential type dwellings. Class 10 are garages and standalone isolated dwellings. Okay, so if we look at the scope limits of AS 1684, we need to stay within these parameters to get the deemed to comply provisions to be working for us. Outside of these provisions, then it needs to move to an engineered solution. So if we look at these scope limitations, essentially the 1684 allows you to design buildings up to 2 stories, less than 35-degree pitch roofs. The building width plan dimension has to be restricted to 16 metres. The eave height has to be less than 6, and the ridge height has to be less than 8.5. And typically the wall heights have to be less than 3.6. Once you step outside of those parameters, then you move to an engineered solution. Okay, so when we look at design bracing, how is the compliant design bracing calculated and achieved? As I mentioned, you can use 1684 and use the prescriptive measures in there. We also provide design software to our fabricators. It's one of the unique components of our offer, and it actually calculates bracing within the design software and provides a report. The other method really is have an engineer provide a design solution for you, but they would typically use AS 1684 anyway. Okay, so some of the principles of bracing design. Essentially what you do is calculate the area of elevation of the building that it projects to the wind. Okay, so for single and double story, you can see in the shaded section, that's the area of elevation that the building projects to the wind. Then you multiply it by these pressure values that are calculated in 1684. Okay, so these are basically just pressure values for each type of wind speed location and for the roof pitch and the building dimensions. Okay, so you multiply those two together, you get the total racking force for the building, and that has to be resisted by the bracing components that form part of the structure. So how this is done, essentially when the wind loads hit the building, they transfer through these diaphragms. Okay, so these are a critical element in the bracing design, the ceiling diaphragm and the floor diaphragm. Okay, so if we look how those are created, essentially the ceiling diaphragm is a large horizontal beam that's formed by fixing plasterboard, believe it or not, directly to the bottom chords of trusses. Okay, so the key thing is they have to be fixed direct to the bottom chords of the trusses. And these really form a critical design element in the structure. Okay, so what happens is if you don't have these ceiling diaphragms in place, the walls become unstable. With the ceiling diaphragm in place, the wind loads, the horizontal wind loads on the building get distributed out to the bracing walls. Okay, so suspended ceilings and those sorts of things can't provide that sort of diaphragm action, so you need to find another mechanism if you have a suspended ceiling in place. It needs to be fixed directly to the trusses. Okay, like any other beam, the ceiling diaphragm performance is impacted by its depth. And how is that calculated? It's basically measured, the ceiling depth is measured parallel to the wind direction. Okay, so you can see here, for these deep diaphragms, you get better engagement of the ceiling diaphragm, and this is measured in the standards by ceiling depth. Okay, so you can see at these lower ceiling depth, the distance between these bracing panels has to start reducing because the capacity of that diaphragm to carry load is reduced. Part of the AS1684 is the bracing wall spacing, so it sets strict limits for the distance between these bracing walls, and this distance is measured essentially parallel to the wind direction. Okay, so in this green direction here, you can see these units highlighted in green form a part of the bracing resistance in this direction, and the distance between them is measured perpendicular to these brace walls. If we turn and look at this other orientation in the yellow direction, then these yellow highlighted walls form part of the bracing in that direction. Okay, and you can see prescriptive measure of the 1684 says that these bracing units for N2 shall not exceed 9 metres. If you look at the lower story, then those bracing units can be have 14 metres distance between them, and the reason that's slightly different is that the floor system is a lot stiffer because it has particle board and ceiling sheet attached to it, so it's a lot stiffer, a lot more stable, and you can go a further distance with your bracing units. So if we look at the types of bracing unit specifications, these are all prescriptively provided in the 1684 in section 8. There's a multitude of them. It really comes down to selecting the right one for the job. There's also a number of proprietary systems that have been developed over the years. You can see here, these are what we call our PWTBs, which is a Pryda wall truss brace. These are just vertically orientated trusses that are fixed down here into the slab, and they essentially act as a cantilever column. We also supply a number of narrow bracing wall units which are outside of the scope of the standard, and these are all specified in our design documents. Okay, so what's brought about these types of units is the fact that the growing demand for narrow width walls, everyone wants open plan living, and that's the current design trend. So you can see in this particular building here, the closest bracing walls are back here on this end part of the building. There's very narrow wall widths available. Okay, so these types of systems have been targeted at solving those types of building problems. So if we look at the different types of bracing systems that are available and what's most cost efficient, usually above 600 mil, the 1684 has a number of available bracing units that are quite efficient. Below 600, the performance of those types of units drops off, and so you move to these proprietary systems then. And then below 350, these types of systems become quite onerous in their tie downs, and they don't become as effective, and so then you have to move on to steel portal frames. Okay, so one of the design intents of 1684 is balanced bracing. So if we just look at a simple rectangular building with 20 kilonewtons coming in this direction and 10 in this direction, you have to provide bracing that's balanced. Okay, so what that means is, if we look at this 10 kilonewton load coming in this direction, you're going to have 5 on this side of the building and 5 on that, then you get the green tick, the bracing's balanced. If we look at the other direction, we've got 20 kilonewtons, got 15 on this side and 5 on this side. So we've achieved the total design bracing, however it's unbalanced because you've got it all stacked on one side of the building. Okay, so that's one of the key value propositions that we have for our fabricators. Where are they adding value? Our design software designs all this automatically. So you get some quite complex building shapes out there. It's very hard to do it manually to determine how the bracing is balanced. And so the software does that automatically. It provides this little indicator for the designers. It has a building centroid, and it essentially looks at the bracing units and how they're distributed around this centroid to make sure that the building bracing is balanced on each side of the building. Another value add that the fabricators have is it flags these distance between the bracing walls. So if it detects bracing walls that are further apart from the standard, it'll give the user a warning and say you need to address this ceiling diaphragm through this section. Another advantage is that the software checks along the perimeter of the outside of the building to make sure you've got bracing, sufficient bracing in those parts as well. So you can see this particular one, as we mentioned, the open plan living, you've got a garage, door opening, window along the front of the building. So it's flagging these walls that need attention because you haven't been able to get any bracing through this section of the building. Okay, so I'll just move on to some site fixing. Generally what you need to have in your possession to get site fixing right is the bracing layout. So each bracing unit should be identified on the bracing layout and its capacity. So you can see down here, all the bracing units are listed and their capacities, and then this layout gives the indication of where they should be fixed on site. Okay. So A1684 has a wide range of bracing units, and close attention should be paid to the following fixing requirements for the actual individual bracing units themselves. And then you've got to fix it to the ceiling and the floor diaphragm properly with shear blocks. And then you've also got to fix it to the slab. So we'll look at each of those in detail as we go through here. So with the actual fixing for the bracing units themselves, it's generally dictated by the capacity of the unit. So you can see two types of plywood units here. One's at 3.4 kilonewtons, the other one over here is 7.5 and 8.7. And you can see the fixing requirements change. So in this one here, the nail spacing is nominated as 150. On this one, the high capacity unit, you can see the nail spacing comes into 50 millimeters and 100 down the side here, 150 down the side. So to get these increased capacities for these bracing units, you have to provide more nails. So once we've fixed those adequately on site, then we need to think about how we're going to get those wind loads actually in from the ceiling diaphragm into the bracing walls. Okay, so the wind load comes onto this ceiling diaphragm in through the bottom cords of the trusses, then it has to get out to these bracing walls to engage it. Okay, so the way we do that is something called shear blocks. Okay, so if we have a look at the shear blocks that are available in 1684, these are some of the common ones. And each of them has a design capacity associated with it. So you can see here, these numbers give the design capacities for these different types of fixings. So we've got screws, bolts, nails. No surprise that the screws and the bolts have a higher capacity than the nails. So then it becomes a question, and there's also, proprietary systems available as well. We do Pryda connector shear straps, which provide a similar type of design to shear blocks. So when we're looking at these types of systems, really the critical outcome is to match the capacity of the shear block to the bracing capacity of the wall. All right, so the way we do that, as we said, the shear capacity is nominated in 1684 for JD5, which is essentially MGP 10 timber. When you're fixing these things, you need to make sure they're hard up to the sides of the bottom cords of the trusses, and you're not fixing these blocks directly to the truss, okay? Because the truss needs to be able to settle downwards between these shear blocks, but it has to be able to resist the load in this direction parallel along the wall, okay? So if we look at this in detail with the bracing unit we looked at before, essentially what you need to do is know the capacity of the unit. So we can see this one here is a strap brace. 1684 says it's 3 kilonewtons a meter. That would also be reflected on your bracing layout. Then you just have to measure the distance of the bracing unit. So once you've got those two details, you can just multiply the two together. It tells you what the capacity is. Then you just go back and just make sure that the capacity that you've got for your fixing exceeds the value of the bracing unit. Okay, so for this particular instance, you'd be looking at fixing these shear blocks with 3 14 gauge type 17 screws into the top plate of the wall. And then we look at fixing bracing walls to the foundation. So why do we do this? Essentially what happens is when you put a horizontal load on a rigid body like a bracing unit, it'll tend to tip over. Okay, so what we need to do is make sure that we fix this into the slab at each end, and we have to think about it in both directions, okay, because the wind load just doesn't come from one direction, it'll come from both. Okay, so you need tie downs at both ends of the bracing unit. So if we look at a typical type of bracing unit, the tie down requirements are highly sensitive to the height and width of the bracing units. Okay, so if we look at a symmetrical bracing unit that's 2.4 meters high and 2.4 meters long, and we apply a load to it, the types of tie downs that you're looking at would match the types of loads that are on here with a symmetrical unit. If we then go and make the wall panel a lot narrower, you can see these tie down requirements become a lot higher and heavier because the mechanical effectiveness of that bracing unit is reduced. Okay, so you get a much more onerous tie down for the narrow bracing wall units. So again, what we need to do is we need to match the tie down fixing for each type of unit. And so we go back to 1684, and what does that tell us? Well, for these 3 kilonewton meter type units for plywood and strap brace, you can see here it says fix the bottom plate to the floor frame with nominal fixing. Okay, so what is nominal fixing? Well, that's also outlined in the standard. You can see here there's a table for nominal fixed members for bracing walls, timber plates to the joists underneath. It's 2 75mm nails at 600mm centres, which is this indicated by this type of fixing here. And then for the bottom plates of the concrete slab, you've got 1 75mm masonry nail or gun-driven nail at the slab edge. Okay, and so that's what this fixing is here. So what happens as the bracing unit capacities increase? Well, it's no surprise the tie-down requirements increase. Okay, so now we've got a higher capacity unit. We've got these 6 kilonewton meter units. They're asking for a 13 kilonewton capacity at 1200mm centres. So how do we do that? We go back to the 1684 and we look at these bridging cleats that are fixed. This is for a first floor system to the joist. Bridging cleats with a bolt down through it. The capacity is 15 kilonewtons. So that matches your requirement for these types of units. And typically fabricators will design for 3 kilonewton meter walls just because those tie down fixings for higher capacity units are a bit onerous. But they'll try wherever they can to use 3 kilonewton meters. It's only in certain circumstances that they'll push to these high capacity units. Other types of fixings are bolts into the slab, so you can see they get 16 kilonewtons, and then you're on to manufactured specified fixing details. Now, if you have proprietary systems, so the 1684 typically deals with solid timber sections. When you're using proprietary systems like floor trusses or I-joist, you default back to the manufacturer's specifications. So you can see some examples here. This is our floor truss system with the bracing fixing for an upper story bracing wall. And here's some typical examples of I-joist fixings. So you can see bolts, blocks, and for perimeter fixings, you've got sheet strap brace on the outside of the walls and nailing into these intermediate blocks. So once you've done all that, you've got to make sure that the bracing wall is fixed to the foundation. And again, it gets back to these specific fixings. We typically don't recommend expansion anchors like dynabolts, because what happens is as you start to tighten the nut on the thread here, this lug pulls up into the sleeve and the sleeve expands outwards. And what can happen as you get near the edge beam for these concrete edges, it'll spoil the edge of the concrete. So we typically recommend anchor screws, 100mm and 150mm anchor screws from Ramset, because they tend to core into the concrete rather than expand them out, so you don't get that blowout at the concrete edges. And why do they come in different sizes? Well, most slabs are waffle pod slabs for residential dwellings. So you can see here at the edge beams, you've got plenty of depth to work with, so you can get the capacities with these 150mm screws. However, the slab for these waffle pods is generally 85. So when you try and fix these 150mm anchor screws through here, they tend to blow out the bottom and you can get some corrosion and water issues underneath your slab. So that's where these 100mm anchor screws are recommended for the internal slab on your waffle pods. So fixing for bracing walls to the foundation using proprietary systems. Again, these are specified by the suppliers. So our details here are from our design guide. You can see the typical types of fixing requirements that are required for these types of units. This one's quite high because it's 12 kilonewtons a metre. So you can see there's a fair bit of work required at the heels here because it needs to achieve around about a 35 kilonewton tie down force. The PWTB2 is slightly less onerous, and again, you've got all these connections specified at the base, so you need to follow those. Some common site issues. This job, as we mentioned, the ceiling diaphragm forms a critical stabilisation mechanism for jobs. So this one didn't have the ceiling diaphragm in place. Some of the shear blocks weren't engaged properly, and it also didn't have enough temporary bracing. So what happened is when they sarked the building, obviously that attracts wind load to the roof, and over the weekend a large storm came in and there wasn't enough bracing engaged to be able to stabilise the building, and it essentially collapsed during construction. Other types of things that are commonly missed on site, you can see here the detail that you'd expect to engage the bracing wall with these shear blocks. It just hasn't been fixed off with the right requirements. There's no intermediate blocking along the top of the wall, and these fixings to the sides of the joists just aren't adequate. Okay, so those are often commonly missed. Simple things like strap brace, the standard tells you have to fix them with a certain number of nails and to each crossing stud, and you can just see here that those haven't been put in place. So pretty easy things, but they're the things that are commonly missed on site, unfortunately. Again, another simple thing, the perimeter nailing for these types of units has to be put in place to be able to achieve these capacities, these design capacities. And so here we're missing all of these nails down the outside of the edge of the plywood. Okay, so those need to be in place. And the fixings through the blocking as well. Okay, so you can see here these nail fixings should be into these timber blocks. You can see in this case they've just missed it because this block isn't in the right place. Okay, so you need to make sure that they're engaged and that these bracing straps or whatever the proprietary system recommends are in place as well. Okay, don't drill or cut or notch any of these types of products. They're structural systems. Cutting out chunks of the plywood when it's in place just reduces the capacity of the system substantially. So don't do any of that. Make sure again, simple things, make sure all the tie down connectors are fully fixed off and in place. And again, we're looking at a proprietary system here. This is the PWTB2. You can see this is the actual technical specification for the tie down at the heels. 2 of these CPAH brackets, anchor screws and screws into the verticals, and they just haven't been fitted off. So you need to make sure when you're putting those systems in place that you're following the manufacturer's specifications. And that's it. Thanks for your time. And if you've got any questions, just post them on the chat, and we'll endeavour to answer them for you.
Hello.
G'day, Mark. How you going?
Yeah, good, thanks, good. Sorry, I missed the first couple of minutes of the presentation, but just wanting to ask a question about your design software. Is there any facility where we can send through a set of plans to you guys and have you come back with some design ideas in terms of bracing?
Yeah, generally we handle that through the fabricators. So if you've got any of those types of inquiries, it'd be best to send it to them, and then they contact us and we can go through the job and have a look for any anomalies. So we generally do that as as part of our work with the fabricators. They'll send us jobs that are maybe a little bit contentious because the 1684 is quite good, but the design, it's 20 years old. It's a document that's nearly 20 years old, and so it's not as prescriptive as it should be for some of the designs that are coming out now. So there can be some challenges stabilising some of these buildings, especially with these narrow walls. So for those sorts of things, you engage a fabricator, they talk to us and say, what are the recommendations for these areas, and we can get back to the fabricator and yourself with some recommendations.
Yep. What about if you're stick framing, are you?
Stick framing, I mean, the principle's the same. You won't get the benefit of the design enhancements with the software, but the basic methodology is the same with stick framing. So you just have to have a really solid understanding of the 1684, what it says and kind of what it doesn't say as well. There's areas there that are a little bit, it talks in pretty generic language in most situations. So you just need to be a bit careful with those, the way that you apply the 1684 at times. But if you were stick framing, you'd essentially follow those prescriptive measures in 1684, and that would still allow you to achieve that compliance side off with the NCC.
I just, as a chippy, I find a lot of times particularly in the domestic world, the plans are very, very light on when it comes to bracing, and it's just left to the carpenters and the builder to come up with that. And if you're not up with it, it can be sort of done incorrectly, and sometimes it gets passed. Yeah,
look, that's a common issue, and that's where we try and help out is that if those areas are sort of found, we can give some recommendations for those sorts of things, because not everything's suitable for timber bracing. You know, we do our best to use timber in all of our designs.
Yeah.
However, there's, you know, the odd occasion when you just have to go to another bracing system, which is normally steel and portal frames. But yeah, wherever possible, we use the most efficient, cost-efficient method possible, but occasionally have to bite the bullet and go to steel.
Yeah, beautiful. Thanks for a great presentation. Appreciate it.
No worries, Mark. Cheers. Have a good day.
All right, unless anyone has anything else there, looks like that's everything for today.
Cool. Thanks, guys. Yeah, I really appreciate you attending today, and yeah, hope you got a bit out of it.
Just before we jump off, got one more question.
Yep.
So how essential is it that each proprietary item, such as a triple grip, is installed with all the nails as per the specs? Can they have a missing nail, or is that going to impact on the fixing?
Yeah, look, generally you always try to follow the specifications that are listed on the design guides. The reason being is that they're tested to those values, so you always try and match those. Now, having said that, you know, you can pro-rata some of the values based on the fixings, but you just need to make sure that you're not, you know, the rating on those fixings will come down essentially. So you just need to be careful. You're not going to invalidate the connection design. So wherever possible, yeah, use the full number of nails that are in the design guides.
It looks like that's covered all the questions that will come up, Ian. So
cool.
Thanks for everyone for coming along.
Yeah, thanks for your attendance, and really appreciate it. And we'll catch up with you soon.